Okay, Nick asked an interesting question today, and that is, how do we go about using calculus to find the moments of inertia? We talked briefly about it before we went on a hiatus, and had we been meeting with normal school, I certainly would have covered this. So it makes sense to cover it now. So in this video, I'll do the first four shapes, and then I'll do another video for the sphere, because the sphere is kind of a unique circumstance. Okay, the first one we're going to do is a rod, and we'll do this in two different ways. We'll do a rod rotated about an axis fixed to one end of it. The rod will have a length of L. We will lay it along the x-axis so that our tiny little element of mass, dm, we will use a linear mass distribution. So lambda is the mass distribution. We'll say it's uniform, and lambda will be equal to the total mass divided by the total length, and it will also be equal to the dimensions of this piece, which is dm over dx. The only other thing we have to specify is what's the radius from the center outward that I'll be integrating by, and of course x will be equal to that radius. So the integral I'm going to model is I is equal to the integral of r squared dm. That's how you calculate moment of inertia. And I have both the pieces. So I'm going to do the integral from 0 to L of r squared, that's x squared, times dm. And if I rearrange this, dm is going to be m over L times dx. I can pull out the constants. So we've got m over L, integral from 0 to L of x squared dx. And that makes m over L x cubed over 3 evaluated between 0 and L. And that's going to make m over L times L cubed over 3. And that makes 1/3 mL squared. And so a rod rotated about one end has a moment of inertia of 1/3 mL squared. Okay. Let's do the same problem, except now we will rotate the rod about its center. So now our rotational axis is right here. We'll still place the x-axis along the rod. So now the length will run from L over 2 to negative L over 2. And we'll use the same elements as before. Lambda is equal to the mass divided by the length, which is also this little element right here. Its mass in its length dx, and we'll calculate the same integral. So it'll be the integral between now it's going to be between negative L over 2 and L over 2 of r squared dm, and that's going to be x squared, and dm is going to be m over L dx. And so it's little changed from the previous one. We'll still have the constant of ml over L outside. It'll still be x cubed over 3, but now it's going to be evaluated between negative L over 2 and L over 2. And when I plug those in, L over 2 cubed is going to be L cubed over 8 times 3 is 24. So we'll have m over L times the quantity L cubed over 24 minus a negative, because when you cube it, it'll still be negative, plus L cubed over 24, and that's going to make L cubed over 12, and then we'll knock off one of the L's. So it's going to be 1/12 of mL squared, and that's the moment of inertia of a rod rotated about its center, is 1/12 mL squared. Okay, now we'll go after some of the planar round objects. The first one we'll do is a ring. So it's an empty ring of dimensions radius r, and the mass is all distributed around the edge. So that will be its mass, and again we're going to do an integral based on that being our element. So this one's going to require a little bit different setup. So lambda in this case is going to be the amount of mass, total mass, divided by the entire circumference of the ring. That's going to be 2 pi times big R, its dimension. And then broken down in terms of this little element, that's going to be dm, the mass in that element, and its dimension is ds, which is an arc length. Now, of course, I'm not really going to integrate this as an arc length. I want to integrate over the angle theta. So how does theta relate to an arc length? Well, remember, we've done this before. It's going to be dm over r d theta. So that makes dm equal to r d theta divided by 2 pi r. So it's m r d theta divided by 2 pi r. So the r's cancel. So we're just going to get m over 2 pi times d theta. So that's what I'll plug in for dm. And in this case, the radius is just r squared, and it's a constant, so we're not even integrating over it. So I is going to be equal to the integral from 0 to 2 pi. As I integrate all the way around the edge, it'll be r squared dm, which is m over 2 pi times d theta. And again, when I pull out the constant, it's going to be m r squared over 2 pi. And then when I do the integral of d theta, it's just going to be theta, and I'll evaluate that at 2 pi, so the 2 pi's cancel, so it just produces m r squared. And that's the moment of inertia of a hoop or a bicycle wheel or a ring, whatever you want to call it. So I equals m r squared. Okay, and then we'll do the solid disk. So a solid disk is actually done as a series of rings. We're basically going to take a thin ring centered about the center, and we're going to integrate from there on out. So if I just take the dimension of that thin ring that's part of the solid disk, the disk has a large radius of r, but the radius of the little ring I'm using for my integration element is little r. And of course, the whole disk has a mass of m. So in this case, I need a surface area representation of the mass distribution, so I'll use sigma. So sigma is equal to the total mass divided by the surface area, which is just the area of the circle. So it's the mass divided by pi r squared. And then in terms of elements, that's going to be dm, that's the mass of the little ring. And of course, its dimensions are that it's a circumference times a little piece dr that gives it its thickness. So it's 2 pi r dr. And notice for the integration elements, I use r, which is the variable. And for the total area, I use big R, which is the dimension of the whole thing. This will also be what I integrate over up to big R. And that's it. I am integrating over the radius, so little r is going to be the radius. So my moment of inertia then is going to be the integral from 0 to r of r squared dm. And in this case, dm is going to be 2 pi r m dr, 2 pi little r m dr, all divided by pi r squared, big R squared. And the pi's cancel, and then I can pull out all the constants. So this is going to be 2m over big R squared, integral from 0 to r, and then the stuff left inside is r cubed dr. And that's going to be 2m over r squared, r to the 4th over 4, evaluated between 0 and r. So that's going to make 2m r to the 4th over r squared times 4, or 1/2 m r squared. And that's the moment of inertia for a solid disk. 1/2 m r squared. So there they are. There's the first 4, or the most common moments of inertia that we use, and those are the calculus definitions of sort of how you derive them. I'm going to reserve the sphere for its own video because it's a little more complex.